Hello, everyone. My name is Jared Longfox from the University of Central Florida. I'm the chair of education and outreach for the AIAA Space Resources Technical Committee. We are the group that puts on these webinars for education and outreach. Audiences, anyone from K through 12 students who are even vaguely interested in space exploration and resources to seasoned professionals who have been doing this their whole lives. We do have, as I was mentioning, as some of you may have heard just before the recording started, um, we do post these videos online, so I'll post links to that a bit later in the talk, towards the end during the Q&A, just so it doesn't get lost in any chat. But without further ado, this month we have Dr. Jorge Núñez from the Johns Hopkins Applied Physics Lab here to give us a talk on one of the instruments he's developing for uh, lunar exploration, material characterization. I won't give any spoilers more than that, but I will be going offline or off camera, and I'll be muting. I'll be lurking in the background. So Jorge, if you need anything, please speak up. I'm right here. Anyone attending in the Q&A or in the chat, if you have access, please feel free to let me know if there's any issues on your end, and we can address that. So without further ado, Jorge, take it away. And thank you for being willing to come here and give us a talk. I look forward to this.
Yeah, thank you so much for having me. I'm really excited to be talking to you and to this group about the work that we've been doing at APL with specifically with the instrument that we have been developing under NASA funding, specifically a NASA Development and Advancements of Lunar Instruments grant, or DOLI. And this one is kind of a mid-TRL uh, funding to develop an instrumentation for future flight missions. And so, in particular, the instrument that we are developing is called AMIM for short, which is the Advanced Multispectral Infrared Microscopic Imager. And I guess I shall share my screen here, and hopefully, folks, oh, there we go. I'll get that showing. Um, but yeah, so this instrument is something that we've developed over the past few years at AIM, at APL, and it's an instrument that is it's a camera, it's a microscopic imager, right? So just like your typical cell phone cameras, like you have here, right? That it images rocks and soils and uses LED illumination to do spectroscopy. So it's a little bit different than your typical imaging spectrometers. But what that allows us is to actually, by using LEDs, we can operate in a variety of environments and lighting conditions, right? By having active illumination. And this will, as you'll see, is that it comes in very handy, especially if you're working on the surface of the moon, right? And especially in the polar regions of the moon, where the lighting is coming in at a very shallow angles, right? Where you have very long shadows, but also if you're trying to explore these regions called permanently shadowed regions or PSRs, right? Where no light actually direct sunlight actually enters, right? And so there, most imaging systems or spectrometers use ambient illumination from the sun to image and do spectroscopy. And so if you are in an environment where there is no light, it becomes very challenging. And so by having active illumination, we can basically operate without any concerns from the light and be able to actually get really good signal from the surfaces, and especially be able to explore these areas that haven't been explored yet. And so AMIM is a new instrument that we think it's a new tool that not only could be used for really exploring the moon, surfaces of the moon, both at equatorial regions all the way out to the polar regions, at the microscale, right? Really being able to integrate sort of that mineralogy with microtexture. But it could also, for addressing really important science, but it's also could be a really useful tool to be able, now as we're going back to the moon with not only with robotic missions, but also with humans. And it could be used as a tool to really help sort of prospect for resources, right? And those could not only be including like resources for regolith, right, to for building materials, but it could also be, especially in the polar regions where there might be water uh, present, that we could also use that water and be able to extract that water that then astronauts could use. And so just to, I want to quickly acknowledge, this is a team effort, right? Any instrument that you're developing is not just by yourself, but it's actually a pretty large team. And so I just want to acknowledge all the members that have contributed to the development of this instrument. And so why do we care really about sort of having something like a microscope or a microimager to be able to understand. I'm just going to minimize my box over here. And what do we care, right? And so as we go with these new missions to really explore the surface of the moon, Mars, beyond, right? And especially multiple cadence, some in some cases smaller, right? You need instruments that really can be compact, but it's also be able to support exploration, right? And especially um, hypothesis-driven exploration in real time, especially if you have humans in the loop. But then also, right, you have a lot of future Eclipse missions that are going, and so there's a lot of opportunities. And so being able to really understand what the surfaces of the moon is and be able to address important questions, but also help with exploration. And so one of the tools that has been actually relatively used in this type of exploration is microscopic imagers. So kind of like the microscopic imagers that have flown on the Mars exploration rovers, such as like Spirit and Opportunity, as well as then Curiosity and Perseverance. Those have what's called like a microscopic imagery, which is sort of what the same of what a geologist out in the field would use like a hand lens. And what that allows you to do is really look at the rocks up close. That's what can you see some of these examples below with, for example, the famous blueberries, right? That was observed by the Opportunity rover on Mars in like 2003, 2004, sorry, 2004 timeframe. But more recently, even with, for example, the microimager, these famous leopard spots, right, and poppy seeds that were discovered by the Perseverance rover in Jezero Crater. And what these are, these kind of indicative of potential um, biosignatures, right? And so that integration of texture with mineralogy is really important, not only for integrating sort of what the context is, right? But of course, for future, really enhancing what we're seeing. And especially if we want to bring samples back, it's really to help identify what are the most highest priority samples that we want to bring to our. Okay, so what is AMIM? So AMIM is a camera that uses LED illumination. It's like a microscope, but it's a multispectral, unlike typical cameras that only image in the visible. And so AMIM kind of combines the power of, of a camera or a microscope with the spectrometers, and kind of like your typical these remote sensing spectrometers from orbit that really collect the light and split it into lots of wavelengths from the visible all the way out into the infrared that can be used for mapping minerals. And so, but instead of applying it from orbit where you have hundreds of meters per pixel, now we're applying it at the microscale where you're really talking about micrometers. And so at that scale now you're able to really map and identify individual mineral grains that are making up not only the composition of a rock, but even identify that what's that relationship. And especially as we go, for example, regions on the moon where you're looking not only for specific resources or specific minerals, right? We would be able to, for example, find those kind of needles in a haystack, but also identify what's the relationship, for example, with the water ice to the regolith, right? Is this water attached to the mineral grains? Is it in between the pores? And so having that ability to map those compositions at the microscale is going to be important. And so we have these goals for AMIM, right, where we're not only being able to understand the mineralogy and this texture to help us understand origin and evolution, right, understand the regolith of the surface, be able to also understand any like properties, right, whether you're what's the porosity, right, are there any effects of micrometeorite bombardment, space weathering? But also understand sort of the composition and distribution of volatiles that may be present on the moon. And then, of course, right, the importance, especially as you get more and more missions that are going to the surface of the moon, is being able, since we're not going to be able to go everywhere on the moon, is being able to connect those measurements from the surface to orbit and what we're seeing. And so AMIM is so kind of here's sort of this artist, it's not quite an artist drawing, but it's a design, right? One design of showing how the instrument kind of works, right? That it's an instrument that is small enough that it could fit at the end of a robotic arm, right? That you can really get up close to look at the rocks and soils up close, and you can image them at the microscale, just kind of as this inset image shows, where we're imaging, and this is actually a false color image, and you'll see it later in my talk of an Apollo sample that was brought back. And looking, we observed it with our instrument, and no, the moon does not look like this. For the most part, it's actually pretty kind of like you see here in these pictures. It looks sort of shades of gray. You might be able to pick out a few grains that are like very light tone, but it's pretty dark. But by being able to observe these minerals in the infrared beyond what our eyes could see, really helps bring out those subtleties and associated with the composition. And like in this image, you can really, things start popping out. And so the instrument actually is able to image at 30 microns per pixel. So uh, basically, we can resolve things as wide as a human, the width of a human hair, right? So very fine grain. And each pixel generates a spectrum all the way from the visible out to 3.6 microns. And I'll get to it why that is important later. But over that spectral range, there's a lot of absorption features, as you see here in this image, that are really we can use to diagnose or diagnostic of specific mineral types. And so because the instrument has quite a number of bands within that, we can detect a wide, huge array diversity of minerals. And so whether you're dealing with igneous minerals, right, which is what most that are found on the surface of the moon, we can detect oxide minerals. We can also detect hydrated minerals, ices. We can also detect as well the presence of organics. And of course, because the instrument, right, has its own active illumination, we can operate both in the daytime and in sort of shadow or dark sides. So that's which gives a lot of flexibility in terms of operations, whether you're operating daytime or if you go in to decide that you want to go into one of these small PSRs, you're not hindered by the constraints of the instrument. And so the instrument, just kind of in the short, is that it's kind of it's a simple, elegant design where it consists of an illumination system composed of multispectral LED arrays, right? And those can be tailored depending on your specific mission and what you're trying to look for, right? But currently, it goes from the visible, right, from 450, so roughly around blue, to 3.6 micron into the midwave infrared. It has adjustable focus, right? So we can image near and far. And what's nice about it is that by adjusting the focus, we can take slices over different distance heights of the sample, and so which can combine to generate a completely in-focused image of everything. And so we can image samples that have quite a bit of topography associated with them, and so we don't need to do any sample preparation or surface preparation. And of course, what also enables the instrument is that it has a high resolution, visible to mid-wave infrared detector, right? That's important to be able to sense those wavelengths at the longer range. And so when we're at a highest spatial resolution, which is 30 microns per pixel, the instrument has a field of view of roughly about 3 by 3 centimeters, right? So that is very much comparable to what we see with the Mars rovers, right? Images, and you can connect those. There is enough field of view that you can connect that image from the surface at the microscale to something, that is either with a human eye or cameras that are on the mast of a rover. And of course, because this instrument has quite a bit of capabilities, right? It can, and it's compact enough that we can fit on any landed, robotic mission, or could also support human missions, right? And you can address quite a bit important, really high value planetary science, as well as be a useful tool for prospecting. And then, of course, since we're going to the moon, right, and we're potentially looking for resources as well, right, is identify samples that you want to return, either analyze on board or return to Earth. And of course, this can be accommodated in a quite diversity of missions. Okay, so this is just some of the wavelengths that we use. And as you can see, we have wavelengths across all the way from the visible out to 3.6. And with these targeted bands, right, we concentrate in some areas, there's more concentration because we're targeting specific absorptions. And there might be slight differences in the absorption features that, for example, around 1 micron or around 2 microns, right? That could be help distinguish between different mineral types. And of course, we also have some bands around the 3 micron region, right? That is important for distinguishing water, right? Or whether you're dealing with water ice, but also other volatiles, right? And so these are just some examples of what the instrument could do, right? So we can distinguish between, for example, olivine, right? Which is, mafic minerals, right? Like olivine, pyroxene, different kinds of pyroxenes, right? Like orthopyroxene, clinopyroxene, oxide minerals, right? So like hematite, right? So rust, right? Which is kind of what we see here on Earth. Not that we think that there's quite a bit of hematite on the moon, right? But for example, on Mars, right, that is much more common, right? Mars obviously called the red planet for a reason, because its surface is quite a bit oxidized. But there have been, recent discoveries from orbit where they might have detected the mineral hematite, or maybe even goethite, which is an iron hydroxide, right? And specifically kind of around the south pole of the moon. And of course, we can also see another kind of sort of igneous minerals. We can also do ices, right? So here's an example spectrum of water ice as well as CO2 ice. But we can see quite other types of ices as well. We can also, while not quite as relevant for the moon, right? The instrument, because of the number of bands that we have, it's just like a spectrometer, we can detect a wide range of minerals. And in this case, right, minerals that form in the presence of water. So for example, like clays and opaline silica, right? And a wide variety of clays, whether you're dealing with like marmerilonite, like aluminum phyllosilicates, or something that's more iron magnesium phyllosilicate. And each one are kind of indicative of how much interaction the rocks have had with water. We also detect quite a diverse set of salts, right? So, for example, where you're dealing like halite, chlorates, right? Carbonates, sulfates, right? A huge array. And again, these minerals probably are much more relevant here to Earth, but also for Mars. We don't, right now, we don't think that we might find salts on the moon, but you never know. And of course, as we're looking to go back to the moon, and specifically sending humans to the South Pole of the moon, where there might be water present, right? Our instrument is really well suited for detecting not only hydroxyl, but also water. And we have quite a number of bands that we can tell the difference with the instrument as to what kind of flavor of water we're dealing with, right? Whether you're dealing with hydroxyl, right, which you see with this black dark spectrum, or you're dealing with sort of molecular water, whether that's absorbed or whether that's inside the mineral structure, which you see here, or we can distinguish whether you're actually dealing with crystalline water, with water ice, which is again shifted. And so that's very powerful. Now, we've seen or observed either water or hydroxyl with um, instruments from orbit, and specifically like M cubed. But M cubed cut off around 2.8, 2.9 microns, right? And so one of the discussions that's been associated with that discovery, right, with M cubed, because M cubed does not see this part, right? You only see this, half of the absorption feature, and so it can be a challenge whether you're dealing with. Oh, sorry, whether you're dealing with water, right, molecular water, or you're actually dealing with water ice. And of course, this range is also really useful for detecting other volatiles that may be present in these permanently shadowed regions of the moon, such as CO2, right, ice, methane, ammonia. But the instrument can detect organics as well. And as we see here, right, where we can, because we have bands around the 3.4, 3.5 micron region, we can also detect and distinguish different types of organics. And so here's some examples, right, of organics convolved to the same spectral range as our instrument. And of course, these are kind of be very different from different types of mineral types. So the instrument is very useful. So this is kind of a design of what the instrument would look like, and especially if we packaged it and try to fly it. Here's some pictures of the prototype that we developed here at APL, right? So here's our illumination system of LED arrays. Here's our optics and the focus mechanism, and of course our invisible infrared camera. And just an example of how sort of the LEDs turned on. And here's just with half the panel showing kind of the electronics behind it, right? But here's just an example of just how the instrument, right, operates, right? It takes images by lighting different LEDs sequentially and then taking pictures just like flash photography. But in this case of just using white light, we're actually using different LEDs at different wavelengths and stitching those images together um, over into what's called an image cube. And so here's just some examples of cycling through the different bands, and of course we're taking a camera that is kind of more focused and divisible. But we were able to even get an image here with 750. Not that the color is sort of this purple, but just because uh, pixels in the detector of the camera that I took the picture with uh, allow some light to go through in the IR. And then this is just kind of closing it. And so this is just a kind of example of the data, right, of the testing that we've done. So starting out, kind of some analog samples we tested out, just kind of demonstrating, right? So like Moon and Mars exploration, Hawaii has these really beautiful basalt deposits, right? And basalts are found both on the Moon and Mars. But of course, some of these have been exposed to water, right? And so it's a little more, some of these regolith grains, which here is an example. This was basaltic sand from the Kau Desert, which is in Kilauea, which is in the Big Island. Uh, and you see that in the near infrared, right? So this is a visible image and kind of the inset of what the instrument saw. We could see the field of view. And you see that we can already start distinguishing quite a bit between different compositions. And so, for example, although the sample is mostly dominated basaltic glass, right? There are grains that are composed of pyroxene and olivine. And so these pyroxene grains appear magenta in these false color composites, right? And so you can easily map them out. And in some cases, you see where there is these grains, the pyroxene is as well as a combination with other types of mineral grains, whereas some of these blue ones are more olivine that appear in this sort of in the infrared. But as you go out further by going out further into the IR, we can actually see, and this is now a color composite of different bands further further out in the infrared, centered around 3 microns. And you can see that these minerals have actually have water associated with them, absorptions. And so as a result, they appear magenta. And so when you zoom in and you can extract the spectrum from these based just from the image, right? You see that, for example, like this here, where this magenta colored grain here, and again, this is in the infrared. Receive really very distinct absorption associated with pyroxene, whereas this other one over here actually is an oxidation. You see oxidation that's happening on top of the grains, right? And of course, again, just for scale, this is 2 millimeter bar, right? So these are really small grains, and the alteration we can see at a really micro scale. But because the sample, right, has been exposed to water, and you can start seeing that there's alteration, so not only there's still some mafic components, right, but oxidation, but you can also see the water bands, as well as the hydroxyl absorption that is associated with phyllosilicates that's kind of on the surface of some of these grains. And in some cases, right, there's also that there's probably some organics, right? There's been some cells, and so we see a CH. Now, connecting to the moon, here's another example of how the instrument could be really useful for not only exploration, but also for looking for potential resources. And especially this one's really very much geared as we're trying to build a moon base in the south pole of the moon. And so this is an example of where we took a high lens simulant, regolith simulant, which is mostly composed of an orthosite, right? So almost 75%. And it's a mixture of an orthosite mixed with sort of glass-rich basalt, which is what you see these kind of dark spots over here. Now, and of course, there's also mixed in with some olivine, minor amounts of olivine and pyroxene. And for the most part, you can see that it's very light tone, right? Just like what we expect would be in the highlands, as well as the South Pole, which is dominated by plagioclase feldspar. But even at this scale, you already can start seeing that there's these sort of the darker spots of sort of the basaltic composition. But what's interesting is that we took the sample and we mixed it with water ice. And these are very fine grained water ice grains, which is what we suspect is on the surface of the moon. If there's water ice present, right, it's going to be very fine grained, and it's most likely going to be intermixed with this really sort of light tone kind of regolith. And so here's a natural color image of sort of what the sample looks like. But blowing it up with, and even using sort of extending it beyond the visible, right, into the near infrared, uh, you can't still really tell apart water ice from the regolith, right? And so this is going to be something that's going to be very challenging, right? Especially if you have astronauts on the surface, or even if you have rovers with cameras that extend only into the near infrared. It's going to be very challenging at these wavelengths to be able to see the presence of water. But with our instrument, because we're able to go all the way out to 3.6 microns, and so we really can characterize that 3 micron band, you can see now that you can start distinguishing the regolith and the water ice grains that really stand out. And so water ice grains is everything that kind of looks blue, purple in this image, in this false color image. And so as we zoom in into that region, right, that box area, and extract the spectra for these, you can see, for example, like 1 and 2, not only do we have really nice absorption feature associated with water, but also we have that big, broad band that's very much a telltale sign of water ice, right? And so that really helps us identify that even though in that previous image, we can't tell the water ice, right, in those wavelength range. By going further out into that mid-infrared, we can really just detect immediately, see where that water ice is. But it's also the nice thing about the instrument is because we have everything from the visible to the NIRR, we can also identify sort of these little sort of needles in a haystack, basically. right? Where, for example, here number three, right, this little area, you see absorption associated with a pyroxene grain, right? In this case, it's low calcium pyroxene. But then there's also an olivine grain over here. And again, this is just a sample that has very minor components of olivine and pyroxene, but because the instrument has this ability to map the spectral the spectra of these grains, we can really target absorption features associated with each of these minerals, and they pop out, right? And so, for example, if we're able to find this olivine grain that here and with this absorption around micron, but doesn't really have much water associated. And in this case, it's not actually with water ice, but it actually has just absorbed water on it. And so, what's powerful about this is that if you were using something like a point spectrometer or something that even just imaging, collecting data from longer distances, right, we wouldn't be able to see that, right? But that's the power of having being able to image and map composition of materials at the microscale is that it enables to not only to identify the major phases, right, that are present, but also those really hard to find, sort of needles in a haystack type of phases that otherwise we would have not been able to find. Right? And this is important, especially if you're trying to do prospecting for resources, especially where abundances may be very, very limited. All right, here's an example. We also had an opportunity to look at some Apollo samples, right? And so this is a sample that was collected from Apollo 14 mission. This is a regolith. And as you can see, right, as you can see, the image is that it's very fine grain, right? It looks kind of gray. And as I was mentioning earlier, right, in the visible, it's still pretty dark. I mean, there's a few here that are very bright, right? Those are probably plagioclase spark grains. But it's only by further going out into the IR that you can really start seeing things popping out, right? And you can see that there's quite a bit of diversity, mineral grain diversity within this small sample and the very fine grains. Again, these are grains that are in the order from 125 to 150 microns in size, right? So this is roughly one or two the widths of a hair, and this actually is uh, area is roughly the size of a postage stamp. And within that, you can see that there's quite a bit of diversity. Not only are there olivine grains over here, there's low calcium, high calcium pyroxenes, we have plagioclase grains. We can also see that there are agglutinates associated with that sample as well. And so that's the kind of power of this instrument is that by being able to deploy this on the regolith, we can not only see your major components, faces that are present in the sample or on the lunar surface, but we would be able to also distinguish those sort of minor phases that otherwise we wouldn't be able to see. Similarly, here's another sample that was collected from on the Apollo 16 mission, right, which is a regolith sample that was collected on Station 2. This is a mature soil that is mostly composed of anorthosite, basalt, breccias, some different mineral grains, and of course, agglutinates. And what you can see is that, again, you have in the visible, right, to our naked eye, it only would appear, right, like you may be able to pick out the white grains, right, and but everything else is pretty dark, right? Um, but by going even to the near infrared, right, we can already start being able to pick out where things that are, in this case, look red, right? Those are pyroxene, dominated by pyroxene. Those are pyroxene grains, and in some case, and those that are blue, like this guy over here, right, that's olivine. And in some cases, as you can zoom in, you can see that there's even, because some of these grains even are breccias, micro breccias, right? You can see this relationship of sort of the pyroxene to the anorthosite. And we can really sort of map it out at the grain scale, and you can get that sort of abundances of what's present. But being able to go further on to the IR really is very useful, where we can also detect whether, right, have these been exposed to water. And so here's the example, right, of this grain over here where it has really nice absorption feature associated with pyroxene, right? Whereas the other one is a little more, um, the blue has a little more olivine to it. But these guys have been exposed to water, where you see here this sort of 3 micron feature where they have the sample has absorbed molecular water on it, right? So I hope that this kind of gives you an idea of really how useful the instrument can be as a tool, not only for understanding and mapping sort of mineralogy with microtexture, and that combination is very powerful, not only for as a geologist, right? That combination is very powerful, not only for petrology, right? To be able to understand what kind of rock it is, what kind of soils it is, but also from an exploration perspective, right? It really can be useful to quickly identify the types of rocks and samples that we're dealing with, but also that look for, specifically if you're looking for certain types of minerals on the surface of the moon or compositions, or in this case, for example, if we're looking for water ice, right? We would be able to see that with this types of instrument. And so that would be very enabling for future missions. And so, as I mentioned, right, AMIM is kind of a really nice, simple design that makes it very flexible, very adaptable, and can be deployed on different kinds of rovers. Where you can go on a rover, it could go on a lander, it can maybe even be used in a habitat, right? And it's because it consists of an illumination system using LED arrays, which can be customized, a focus mechanism that allows us to not only image near and far, but also it allows us to look at unprepared surfaces, right? Whether you're dealing with a really quite a bit of a rock that has quite a bit of topography, or just a regular surface that doesn't need to be sort of flattened. And of course, we have a uh, really broad spectral range visible infrared detector. And so AIM not only provides fine scan imaging, right, which is important for characterizing grain shapes and morphologies, right, but we can also look at textures, fabrics, porosities, right, again at a microscale, which is important for understanding regolith properties, the properties of the surface of the moon. Uh, but it also combines fine scale mineralogy, also again with the same instrument that we can detect key mineral features, right? Key minerals, whether you're dealing with igneous minerals, right, like plagioclase, feldspar, olivine, pyroxene, rock-forming minerals. We're dealing with oxide minerals, right? Any if you have maybe if there's any hydration, right? Salts as well as ices, and of course because the instrument has absorptions that are useful for not only mineralogy, it could even be used if there's organics, right? That could help be used potentially if there's been any cometary contributions at these in the polar regions. And of course, by having active illumination, we can do daytime or night, day or night operation, and we can do multispectral imaging near and far. And so AMINS really combines the capabilities really of what typically is associated with a remote sensing instrument that's in orbit, that's much larger, but being able to apply it, right, make it compact enough that it could be used on something like a small, at the end of a robotic arm, or a rover body, or even like a globe box, right? Something that could be really useful to supporting not only robotic missions, but also human exploration. And so, because it does this without having to do any sample preparation, right, it could really be useful for characterizing the surface of planetary enabling exploration, can use it for prospecting, but also as a tool, right, as a first look to help identify and prioritize samples that you want to maybe collect for analysis with onboard instruments or for returning for. And with that, I just also want to thank again folks on the AIMIM team. Also, we're collaborating with the Dragonfly mission, and some of the technology that is developed with AIMIM is actually going to Titan as well with Dragonfly, and then of course also NASA support. With that, thank you, and yeah, happy to take any questions.
Very cool. Thank you, Jorge. Uh, I love this instrument. I know we've talked
Thank you.
about this a little bit in the past.
Yes.
I think it's great. So yeah, thank you for lending some of your expertise and time to this. We do have a few questions in the Q&A.
Yeah.
And hopefully we have time for me to get to one or two as well. But I'll take attendees first. Andrea Rotoloni asks, have you done cyclotron tests on system on chip to simulate radiations in which the chips are exposed? To simulate silicon crystal damages on AMIM and understand the spectrometer's working life, as well as to measure radioactive isotopes.
Yeah, those are really great questions. And so yeah, radiation, right, is one of the things that is ex expected, right, on the moon, right? Once you get outside of that, the Van Allen belt, right, that protective shield, right, that we have here on Earth. So we have done radiation testing on the LEDs, right? We've done both with gamma rays, but we also have sort of ionizing radiation with particles. And to see what kind of damage, as you mentioned, right, that there's, in the band gaps, right? Now, this might be getting a little bit too much into the details of the physics, right? But just like with detectors, right, that radiation can damage and destroy sort of the lattices, right? And so it reduces the efficiency of whether the detector, but in this case, it would be the LEDs. And so these LEDs are kind of more radiation hardened or kind of next generation. And yeah, so we've done testing with radiation, and while we've seen a little bit of drop of radiation, but that's after because we're using the same LEDs that we're using for Titan on Dragonfly, to send to Titan with Dragonfly. We've subjected them to basically 14 years worth of radiation. And we've seen on the orders just, like a few percentage. Um, Now, there's also mitigating approaches that you could do to reduce the effects of radiation. Some of them being, for example, we can put a little more shielding behind the LEDs, right? Because again, most of the time the instrument is going to be looking down at the surface or at the sample, right? And so you can provide additional shielding around behind backside so we don't get as much sort of exposure to the radiation environment.
Awesome. Very cool. Not surprised at how rigorous that characterization was. We don't have any in the Q&A right now, so I do have one, but while I'm thinking about it, I'm going to put in the chat for everyone a link to the AIAA Space Resources webinar, the Space Resources YouTube channel. I'll ask my question, then I'll post one more link in the chat. So I get it, this is almost an unfair question, but and I'll narrow down scope. What if you could choose one location to send this on the moon,
Oh gosh.
where would you go?
Oh my
And
gosh.
it doesn't have to be the most scientifically informative. It can just be your favorite geologic site on the moon. Uh, you have your pick.
Oh,
Science and funding aside, where are you
science
going?
and funding aside, gosh, I mean, I would love to take it everywhere. I mean, seriously. Everywhere on the moon, because it is so powerful and it is so enabling that it's like, you know, I mean, we could go to the poles, right, and really understand the question about the water and what other volatiles are there, right? And that's the reason why we designed the instrument to extend that
Mhm.
broad into the midwave infrared, right? Because we really wanted to be able to see water and also, what kind of water is there, right? Because that's a source of big debate or discussion, right? Is what's the type of water that's there, right? What's the origin of that water, right? And that, of course, has big implications as to the origin of water here on Earth as well, right?
Mhm.
And so, yeah, so I would say probably the South Pole, but I mean, there's so many really cool, interesting places. So, for example, like maybe Aristarchus region, right, where there is volcanic and there might be also indigenous water, right? there's some pyroclastic deposits that they might have seen some OH absorptions with from orbit, and so that seems like a geologic wonderland there as well.
If I had one place to send this, it would be Aristarchus. So,
Yeah.
great minds, I suppose.
Yes, exactly,
Um,
exactly.
and then, folks, feel free to punch in the Q&A. I am going to selfishly ask another one. One that you always get very interesting answers from instrument leads. What was the most surprisingly challenging part of this development? What did you go in that was hard that you did not think was going to be?
I mean, I think, the I think the biggest challenge was really trying to have an instrument that could image over this such a broad spectral range, right? And especially with one camera, one set of optics, you know, most times, right, when you're dealing and of course getting that high spatial resolution, right? That was a challenge, right? We were really kind of pushing, I wouldn't say pushing the limits, but we were definitely kind of sort of walking towards that, right? Because it is, especially as you go into the microscale, right? That's why microscopes tend to be like invisible, or if you right, you're limited by the wavelength, right? And so if you want to get even smaller and smaller, in some cases you have to go to X-rays or things like that. Um, and so and the challenge is that it was not only being able to look at samples up close, right? Have that 30 micron pixel spatial resolution, right? But also over that really broad spectral range. Because most instruments, right, even from orbit, right, most cameras, right, they operate kind of in the visible infrared range, right? There are other instruments that operate in the IR, right? And so you would either use two different instruments, right? Or if you're using one instrument, you would use two different types of detectors, right? You would split the light into two set of optics and detectors, right? One is visible, one in the IR, and then one that's kind of shortwave infrared and longer, right? And so we said no because we wanted to keep it simple or a complex, simple design, but also be able to keep it small, right? This instrument, right, is much smaller compared to a good number of instruments that have that similar type of spectral range, right? But they operate from orbit or things like that. So,
Uh, well put. And now I will remind everybody in the webinar chat, I've posted the link to the YouTube channel and the AIAA Engage page where we upload the slides from these. If the AIAA Engage page, you do need to log in, but it's a free email. Like it's just sign up with an email. It's not a paid thing. You don't need to be an AIAA member. Just FYI. And my last question before we wrap up here is this this sort of development that you've done is so mass optimized, so size and power optimized that it lends itself well to being included as a more comprehensive suite of science instruments. Um, if you had to pick one other instrument of any kind to send with this to do science at any site, what would you pick to pair with this?
that's a tough
And
one.
just one instrument.
Just one.
That
Oh God,
that's what makes it
that's a
tough.
tough fight. Well, so with this instrument, it does a really good job at getting mineralogy, right? We can detect almost a huge swath of minerals, right? And of course the microimaging, right? But one thing that is that we that we're kind of would be very complementary, right? Is pairing it up with something that will give you elemental composition, right? This could be something with like an XRF instrument, or it could be like a LIBS, right? Or something that gives you elemental composition, right? So,
Mm.
because with our instrument, right, we could tell you that there's pyroxene, we could tell you that like olivine, even distinguish between whether you're dealing with iron-rich olivine or magnesium-rich olivine, right? But we probably can't really, it'd be more challenging to be able to tell what percentage or what type, what abundance of that element is, right?
Yeah.
What is your specific iron magnesium ratio, right? Or for example, right, if you're dealing with water, right, we can't tell whether you're dealing with hydrogen or deuterium, right?
Yeah.
So, so something that would give you elemental abundance, I
Yeah.
think would be really valuable. I think would make a really really powerful complementary payload suite.
No, and perfect answer for a geoscientist. And
Yes.
well said. So we are getting towards the top of the hour. Um, I don't see any others in the Q&A, so I guess I'll start to wrap up here. Again, Jorge, thank you so much for your time putting this presentation together, developing the instrument just to come here and talk to us about it.
Oh, thank you so much. Yeah.
Yeah, I look forward to seeing this thing manifested on lunar flights, on Dragonfly,
Fingers
and
crossed,
much,
hopefully.
much more. Fingers crossed.
Fingers
So
crossed. Yeah.
yeah, everybody, thank you again for attending. I'll have this recording up on YouTube as soon as I can. Jorge, I'll send you the notification for when it's up. Everybody
Yep.
else, feel free to keep an eye on the
And
YouTube channel over the next couple of
yeah, and
days.
then if
And
folks have questions, I was just gonna say, if folks have questions, my email is on the my slides, right? And so folks, if they have a question, they can reach out to me.
sounds great. Awesome. Thank you again for your time. This is a really cool presentation. I appreciate it.
Yeah, thank you so much for the invitation. Really
Of
happy
course.
to talk to your group. Thanks,
Of course. Bye, everyone.
for everyone.